Hello, welcome everyone. Today I will look at the Rosetta Code website and solve some tasks that are not implemented in Mathematica yet. So here's the Rosetta Code website, and here we have all the tasks for Mathematica that are already implemented. So these are 1127, a lot of which I've done before, but there's new tasks coming all the time. So here's a list of the tasks that have not been implemented in Mathematica yet. So it's a reasonably big list. And I selected a few already. So for example here I found a couple which I will try to solve now. So let's look at the first one. So the idea is to create a program that crashes as soon as possible, with as few lines as possible, code as possible. Be smart, don't damage your computer. Code should be syntactically valid. Okay. Otherwise, you could just trigger a compiler crash, for example. It should be possible to insert in another program. Okay. So what do other people do? So that's always a good way to have a look what other people do. So asserting certain things, that's of course a nice way of doing it. Division by zero, so that would not work with Mathematica. So let's open a new notebook. I'll make it slightly bigger. So if I do 0 divided by 0, we'll just say indeterminate, but it will not crash, let's say. What do other people do? Segmentation faults, okay. I guess, what do they do in C++? Let's see. Okay, they also do a division by zero, or they throw a runtime error in C++. Maybe there is a Python, there we go. Also division by zero, okay. So the first thing I'm thinking of is just doing abort, which crashes everything. But maybe, yeah, I guess that is I'm not sure what assert will do. So the truth has been enabled, there's encountered, there's no assertion failure is generated, but I don't think it will stop the evaluation, or will it? No, it will still return something. So I think abort is perfectly fine here. So let's add that. So Mathematica will just go above nim. So I have a little notebook that helps me in copy these headers, because I'm lazy. So here the code will be very easy. And well, it's not really an output, so we can just say save this one, and then I'll take a few seconds, and then we have a new entry, Mathematica / Wolfram language is in this case the same, abort, and that will do I think what the task requires from us. So another one done, 1128. So I selected just a few more, let's say random ones. So let's do these ultra useful primes, for example. An ultra useful prime is a member of a sequence where each an is the smallest possible integer k, such that 2 to the power n minus k equals prime. K must always be odd, since 2 to any power is always even. Yeah, so this is always even, so if this has to become prime, this has to be odd. Find the show here on this page the first 10 elements of the sequence. Ooh, so the immediate problem I see. Well, let's do it in this one. That 2 to the power 10 is a pretty big number, right? Okay, so how do we do this? I think I will just subtract k, increase k, and then find the first one that is a prime. So let's do a table. Well, I can make a function, let's say. find k, find ultra useful prime k, and the input is n. So the number that we're interested in equals 2 to the power n. Alright, now we subtract k from this. So k goes from 1 to infinity in steps of 2, so it's odd. If prime q num minus k, okay, then we break this. But before we break that, we just assign it to some variable, temp or something. Here we go. And then we return temp here. Let's make temp a variable here. And because I'm paranoid, let's add this. So now, let's say, I don't know, 6, 59. So let's look here. 1, 2, 3, 4, 5, 6. That looks pretty good. Well, do immediately. Is 0 included? People don't seem to include 0. Okay, so start counting it. N equals 1 in this case. So 1, 3, 5 seems to be correct. So they're asking for the first 10. Okay, that seems pretty fast. So there's also a stretch goal. Find and show the next several elements. The number gets really big, really fast. Only 19 elements have been identified as of writing. Okay, I think we should probably do something like this to see what is happening. Let's do 12. Okay. 13. Okay. Of course, I'm doing 1 to 12 again. Let's see. What do people find? 10. People find up to 13, but the k goes up to several thousands. I don't know if this is 12 or 13, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I found the first 13. I'll do 13, 10. Oh, here's one. So in Ren, people found 14. Well, I think what we can do is do this, parallelize it. And let's do just a snippet here so we know what is going on. And let's make sure it does the finest grained. So this dynamic doesn't work anymore. But now, oh, it's running many kernels. It uses 10 kernels, it's okay. And of course, these will take much longer. I have no idea how long 14 will take because those numbers are really, really big. Maybe I should test that out first, just 14 by itself. Not sure if we can do 14. Because 2 to the power 14 is really a gigantic number. Okay, doesn't seem too bad. Oh. Let's see. Oh, this is K now. Oh, so it will take a while until that is 13,000. Oh. I don't have the patience for that, so let's just do 1 to 13. If someone wants to calculate 14, well, that's fine, they can do that. And let's make this code as, let's say, as small as possible. But it still runs. So like this, of course, this print statements are not needed. And then let's call this results. And now we have to show this. So what we can do is we can do table from res. They say table headings automatic. So we have a nice little table. I think that is good enough. So let's add this again to the code here. So Mathematica will be just above Perl. So we'll edit the entry of Perl. So here's our code. So let's save this. Rosetta ultra useful primes. Here we go. So let's copy this. So nice indentation going on. Oh, and this line for giving the output. Here we go. And let's put a semicolon there. Yeah. So then here, I think we can copy this quite nicely. Here we go. Let's just test this. If this is correct. Okay, this all looks perfectly fine. Save page. Alright, another one done. Now, let's do periodic table. Display the row and column in the periodic table of the given atomic number. Let's consider the following periodic table presentation. So element 1 is at place 1, 1. Okay, that's hydrogen. Element 2 is row 1, column 18 is helium. And then, well, there's many more. Details. The representation of the periodic table may be represented in various ways. The one presented in this challenge does have the following property. Lanthanides and actinoids are all in a dedicated row. Hence, there is no element that is placed at 6, 3, 7,3. You may take a look at the number representation here. Okay, you know, that number is at least 1 at most 118. So we do care also about the. Okay. All right. I think this should be included in chemical data, or no, element data actually. Element data. So let's look at the help. So the end chemical element, and then let's see. So okay, which one is oxygen? 8, let's say. 8. And then let's look at the group. 16. That seems to be correct. But what about neodymium? So 60. And does it know the group? Okay, for 60 it's undefined. And the row yes, the row is correct. Okay. Oh, this one. So let me see. So from 57 to 70, the group are not defined. Okay, it's kind of weird that but we can find period and group. So let's make a little function. If n is smaller than no, if n between let's do it the other way around. Let's do it like this: 57 to 70, or 89 102. Then we have to do something special. Let's do it like this actually. Perhaps I can use switch or which expression for value, then which test value, test value. So let's see, and smaller equal than 118. True. Element does not exist. I think it's just a string, right? Yeah. Yeah, sorry. 1 should be right. So yeah, so here we can just do element data. And do we want row column or column row? So helium should be in the 18th, so it should be row column. So I think the column is called the period. We can test it out, of course. Let's just it now. And then helium we said, so that's 2. Sorry, I have to of course put n here. 1.18, yeah, so a period in group I have correct. So if it is between 57 and 18, so let's do 58 as an example, then the period, the group is not defined in this implementation, but we can just set it to be, so it says that it is still in row 6 in the implementation of Mathematica, but in the definition here it basically says it is on a separate row. That's fine, but we can do 8. And then let's see, we can just say the column is the number minus 54. Right? 53. 57. Neodymium should be in the, no, what's 58? 58 is cesium, I guess. Wait, I'm confused now. Cesium. Just make sure that I do this correctly. So 58 should be 8.5. That is weird because here it's 4. Okay, that is peculiar. Okay, so I think well, let's implement all of them. 1, 2, 29, 42, 57, 58, 72, 89. So, first one correct. 118, 411, 56, 84, 85, 64. And then that little, I think this would be something similar, but now with 9. And of course we have to subtract a different number. 89 equals AC. I don't know what element that is. Oh, it's 8K here, surprisingly. That's also surprising. So I should subtract 85, right? Yeah. So what do we have to output? You may take, at least one, at most 118. Okay, lookup table. Some people implement it differently, of course. But I'm curious what people output as a free basic. So what I anyhow can do is this, and then oh, it might be fun to do a beast of text. So text is expression and coordinates. It's row column. Okay, let's reverse that just to, and then, well, it's a bit, the coordinate system goes down here. So what I can do is do this, and then actually I have a little mini representation. I think this is, well, maybe a valid output as well. I don't know what they exactly want. But maybe they just want to see these. I'm not sure what people show. So people show this list. I'm not sure. So let's do that list. 1, 2, 29, 42, 57, 58, 59, 71, 72, 89, 90, 103, 113. Well, yeah. Element. Boop. Turn it into a row, and then of course we need a column here. And let's add some spaces. It's pretty good. Let's add this. So Mathematica's Perl. Okay, here we go. Can we make this any shorter? Well, we don't need the module in fact, so that will save us a few lines. Let's just copy this. Right, so this should be able to be, let's do input text, I think. No, not input text, plain text. Plain text, sorry. I don't want to screw with the other solution. So this will be 1, and then graphical representation of the periodic table positions. I'll just click it here in, because this is a piece of graphics that I can of course not export here, so I will just put it here between brackets so people know what it will kind of do. Let's see what it looks like. Okay, looks all pretty good. Maybe I can put a little note in the beginning. Mathematica and the Wolfram language include the period and group in the function element data, but does not, but has a slightly different, has slightly different definitions for the, what was the word? For these two. I don't think this is named after someone. Okay. All right. Let's save this one. All right, another one done. So, but just to give you an idea, so here I made some code that can request what tasks have been done. So 1130 now, because we filled in a few. Or for Mathematica, well, if I rerun this now, it will also be 1130. I can also request what have not been done yet for the Wolfram language. So 168 tasks are open. And for Mathematica, there are now 140, I guess. Yes. So for each one of them, I can click here now on these, and then I go immediately to that website if I'm interested. So that's kind of useful. And here, this little bit of code is just that I can copy these headers that I use. So it's always consistent, and I can easily copy these headers. So I can open the not implemented page. So this is the page I showed you before. So this is slightly shorter now because we filled in some. Copy the Wolfram language header or copy the Mathematica and Wolfram language header. So these are just a quick notebook that I sometimes use. All right, which one looks interesting? Prime gaps. I've seen a few videos of that in on the number of Halt channel. So let's try to do that one. So okay, do we want to save this? Let's save it. Rosetta periodic table. Let's call it that. Right. So let's make it bigger again. Let's call this Rosetta prime gaps. Well, difference prime gaps, something like this. When calculating prime numbers big and 2, the difference between adjacent primes is always an even number. Yes. This difference, also referred to as the gap, varies in a random pattern at least. No pattern has ever been discovered. This task involves locating the minimal primes corresponding to those gaps. Though every gap value exists, they don't seem to come in any particular order. For example, this table shows the gaps and the minimum starting value primes for 2 to 30. Okay. On 0 prime gaps that differ by exactly 2 to be adjacent. For each order of magnitude m, from 10 to the 1 to million, find the first 2 of adjacent minimum prime gaps where the absolute value of the difference between the prime gaps start values is greater than m. So let's first fix this typo here. So that's the fun bit of this thing, that we can modify this and improve the website. Okay, let's look where. Here we go. You're welcome, Mr. Rosetta. Okay, so now not many codes have solved this, but let's look at C++, for example. let's first calculate some primes. So let's calculate the first, let's say 1000 primes. Right, so the gaps we can calculate. Now we can associate each of those gaps with their, well, let's say the first of these two primes. Here we go. So the gap is the first number. So let's gather them by the first, which is the gap number. And we only want the first ones. So if I do this now as a grid, then the gap of 1 is at 2. Gap at 3, 7, so 10. How do I do this? How do I interpret this? Earliest difference, then the gap 4 started at 7, gap 6. Adjacent prime gaps. Adjacent prime gaps. So I want to do the difference of those then. Right? Do I understand this correctly? So what we do? We have the adjacents. Locating the minimal primes corresponding to those gaps. That between two adjacent primes there will be a gap corresponding to. Not sure if I understand this fully completely. Let's say. So the difference here. Gap 14 starts at 113. Maybe you can do a little bit bigger. Let's call this. Yeah, I think I want to do the difference now. These numbers. 1,2, so let's do the differences. Differences of those, and most of them 1,1. So the first one 10, above 10 is this 4. So this is the 4, a gap 4, yeah, and the difference is 16. Here we go. Now 100, so that would be the difference between adjacent prime gaps, starting primes. Gap 14 starts at 130. Okay, I see the problem here. I have to sort by the first column, because otherwise it does not really work. Sort by the first. And this will make a lot more, makes more sense. And then probably I want to do the absolute of this, right? Yes. So the first one above 100. Yes, I guess this one. First one above 1,000 is the same one. 10,000 is 36. Yeah, okay, so let's call this my set. So what we're going to do is now select first actually from set, where the last is greater then 10 to the power I, and I goes from 1 to 4, let's say. So this will be 10 to the power I. So this starts at gap 4. The difference is, well, gap 6 of course, so this is always 2 different, I guess. Yeah. So what do we want to find? The first set of adjacent minimum where the absolute value of the minimum is greater than m. So this number is the size of the gap. Yeah, so I can request, so if I have this list here, I can turn it into rules and then into an association. So these are starts. And then let's call this n comma k equals that. And n comma n k, and here it will be, what do they call it? Starts n. And then n plus 2 starts n plus 2 and k. So if I understood correctly, I have all the ingredients here: 114, 113, 16, 17, 18, 14. But now, so m should go to 10 to the 6. I mean, we can do, I don't know, let's say the first million primes. I'm not sure if I want to, okay, that's not too bad. And then here, I guess I can do this. Oop. Let's see if this one is correct. So gap 100, 296,733, not 2. And the difference is 1,047,000. Okay, let's try one bigger. I guess this will take a second to calculate. Oh, and this one will also be pretty big. That's fine. All right. Oh, now I can do one more. 10 to the 7. Is that correct? Seems to be correct. All right. Okay, now let's make let's call this our data. Do we want to use string template? Never used it a lot actually. Can I also give it what was that? There was an taken. Okay. So let's just be lazy and copy this. And then, so here, this will be the first number. Let's make this slightly bigger. There's the enter here. So, and third, fourth, fifth, sixth. And then here we do data, I guess. Let's say this is a print, because why not? String, how does this work? Ah, yes. Of course, this is, we should do it like this. And then we can do this because we don't need to output, well, this map, we don't care about the values. Yeah, I think that is fine. So let me just double check if everything is correct. For example, this one. Yeah, it seems all correct. So this one, so let's, oh shit, this takes a long time. Kill it. Stop. There we go. I'd say that's a pretty short code. Let's add this to Pascal. Oh, I need the other code first. In the header. Let's copy this. Let's paste it. Okay, this is not so nice. I mean, it looks pretty annoying. And then let me run this one more time. Oh, so save this. Okay, that was too fast. So here we go. It's still executing, but it already printed it. That's a bit weird. Plain text. Let's do a preview. I mean, this table is on 2 lines, but maybe that's better for readability reasons. Yeah, that space. Oh, that new line. I think I will kill it. Here we go. Save page. Right, solve one more. So what is this about? Pisano period or Pell numbers. Ooh, there's a lot of little subtasks. Let's do Pell numbers. Let's make a little new notebook. Oh, by the way, you might have seen that this is the new version, 13.1, that I just downloaded some days ago. And that was just released. So let's save this. Rosetta Pell numbers. Here we go. Now, Pell numbers are an infinite sequence infinite that comprise the denominators of the closest rational approximation to the square root of 2, but have many other interesting uses and relationships. The numerators of each term of rational approximant to the square root of 2 may also be derived from Pell numbers, or may be found by taking half of each term of the related sequences, Pell Lucas or Pell companion numbers. The Pell numbers are defined by the recurrence relation blah, or by this closed expression. So, I mean, the first task will be to compute the first 10 Pell numbers. So let's just, let's call it Pell number, or Pell. Let's call it Pell number of n equals 2 times Pell number n minus 1 plus Pell number n minus 2. And then we have, let's say, some initial conditions. We can do this. 1 equals 1. Let's make sure we clear those. Okay. And then the first 10 correct. Let's see what people have. Oh, a lot of output. Okay, so they started counting at 0. That makes sense because of this. But then the first 10 are ending in 985. The first 20? Did I misread it? Oh, he does 10. He does 20. We can do 20, I guess. So the largest would be 6 million. Yes. Okay, but let's stay to. Okay, so that's the first part of the exercise. Find and show at least the first 10 Pell-Lucas numbers. Pell-Lucas or Pell companion numbers are defined very similar. It's the same, but now it's 2 instead of 0 1. Let's just call this Pell-Lucas number. And then this becomes 2. And then let's see. 2, 2, 6, 14, 34, blah blah. Okay, that all seems good. Use the Pell and optionally Pell-Lucas numbers sequence to find and show at least the first 10 rational approximants to square root of 2 in both rational and decimal representation. Okay, I have to read a bit. The sequence of rational number to the square root of 2 begins like... so I think... Let's call this Pn. Let's call this Pln. Because we are multiple... Let me clean this up a bit. And if I understood correctly now, is this what I want? The sequence of... Starting from M1, for each term, the denominator is Pn, denominator, and denominator is Pns, and numerator equals Qn over 2. And now we do numerator over denominator. Okay. Starting from n equals 1. Okay. Okay, let's do the rest of this. So those are the fractions. So these are approximants. And then here we do approximants. Here we go. So yeah, what we can do is well, it's fine like this actually. Find and show, find and show at least the first 10 Pell primes. Okay, what are Pell primes? Pell primes are Pell numbers that are prime. Pell prime indices are the indices of the primes in the Pell number sequence. Every Pell prime index is prime. Though not every prime index corresponds to a prime Pell number. Every Pell prime index is prime, though not every prime index. Not sure what they mean with the prime index. Anyhow, we can calculate the first Pell numbers. Let's calculate the first 100 or so. Oh wait, maybe that's a very big number. Yeah, because it kind of doubles every time. But you should be able to do 40 maybe? 30? I'm not sure how big these numbers get. Pretty big, but what we probably because it takes so long is because there is now memoization. Here we go. now we can calculate them much more faster because it memorizes the in-between numbers that I calculated, so I don't have to go down this recursive definition all the time. So which ones are prime? And now we want the position of the true elements. So what do I want? The first 10 Pell primes. Pell numbers. Let's do that again. Select. Can I do? I can do select. Say 3 arguments. So we do prime q and then 10 it said, right? First, yeah, up to 10. Okay. How many do we need? 10. Oh, it needs 10. Okay. Well, we can go a little bit higher. Let's say the first 100. Are these 10 now? Yes. Okay, now I'm kind of curious what position this is. 90. Okay, so we need 100 terms roughly. So these are the Pell primes, and now the indices of where these are. So what we can do, maybe it's a bit, I mean, yeah, let's see, these are 2, 5, 29. It depends, of course, if you start counting with 1, 2, or 3. So this is starting from 0. So this is the third, which is actually the second element. So I should probably, what I should do is do this, and then the last one is a prime. And then I have the index, the index and the prime itself. And then let's do only the first 10. Here we go. Now, so we have the Pell primes. And now we want 10 Newman-Shank-William numbers. What the hell are those? So let's save this, by the way. If you take the sum S of the first 4n plus 1 Pell numbers, the sum of the terms P2n plus 1 will form the square root of S. For instance, the sum of the Pell numbers P5 is 49. Is the square root? Is the square of P2 plus? Okay. The sequence of numbers formed by the sum P2n are known as the new NSW numbers. Okay, so I have the PNS again. Let's do that again in a slightly different format. So I have a first. So this will not come to me anyhow. So s of n is P&S up to 4n plus 1. And then the total of that. And then is the square of, okay, so we can do the square root of that. So the numbers are correct. 0 works, 0 works. But of course it's neater to use this property, because then I don't have to sum up, you know. What I can just do is say, so this is nice, but nicer is to do let's see if that is 4n plus 1, and this is 2n plus 2n plus 1. Okay, then is this correct now? Oh, so if I put in 0, is this correct now? I have to code it in a bit in a hacky way, but that's fine, I would say. First 20, okay. Oh, it's a big number. Is that the same as I have? I'll have to do 19. Is that the same? Yes. Okay, so these are the PWS. Sorry, NSW numbers. Okay, then find and show at least the first 10 Pythagorean triples corresponding to near isosceles right triangles. Pell numbers may also be used to find Pythagorean near triangles with like on AG 3, 4, 5, yeah, 20, 21, 29. For n bigger than 0, each right triangle hypotenuse is P 2n plus 1. The short leg length is the sum of the terms up to Pn 2 plus 1. The longer leg length is one more than that. Okay. Let's call this. Okay, so you first need a little database again. Pythagorean triple n. Input is an integer. Okay. Hypotenuse. Let's call it hypo. Is P&S 2n plus 1. Short, long. Short is the short is the sum of the terms up to. So I would say no plus 1. We total this, and long equals short plus 1. And then we have short, long hypotenuse. clear, kill this, and then okay, let's do this at range 10. And let's just make sure this is correct. So let's call this solution, and then what we want to do is number 1 squared plus number 2 squared minus number 3 squared. It's all 0. That is very satisfying. Yes. Okay, but we don't need to do that. We just need to find the... So this is a bit of a messy problem, I would say, because it has these, what is it, 6 or 7 sub problems, let's say. So I like to always put all the code in one little bracket, so people can run it in one go without what I could do is just move this like this. For efficiency, do I want to do this? It is a bit nicer. So this is a bit nicer because then I don't need this definition. And the same holds here, kind of. Pell number 2n. So I don't have to pre-compute this. So this was the acetal and SW, whatever it was. So 1, 2, 3, 4, 5, 6, 7 outputs. Very good. So, not many solutions are there actually. Let's do. So there's also someone really active in Perl. Many people have Perl and Wren are very popular on this website. So let's copy all this code. Copy. Paste it in place. I think everything went fine. We'll remove this enter. Remove this enter. I think everything is pretty readable. I like this being like this. And the results, you can just copy. Boom, boom. Okay, it's not all copied so nicely. Copy as plain text for the table. So this grid doesn't work so nicely. Sometimes it automatically enters 1, 2, 3, 4, 5, 6, 7. So here we go. And then pre. Yeah, it looks pretty good. Let's have a look. That looks, well, it will be scrollable, but that is fine, I guess. Let's save it. Alright, so I think I solved like 4. I think we'll stop right here. If you also want to contribute, you can go and find, well, you can actually find this website. Task not implemented Mathematica, and here's a list now. It's like 100 or so, and some of them are more complicated than others. and but generally they're very much doable. But some, like this one, for example, is quite tedious to implement. So I haven't gotten there yet. But also there's continuously new problems being added here. So every once in a while I come back and see and contribute. Because as you can see, my contributions so today we contributed these 6 ones actually. Oh, here's a typo, so 5, sorry. We have done 5. So around May I contributed some, but then it was 2021. I did quite a few, as you can see. So you see, I have made many contributions over the years. I think I've did even much more than. So here, 2009 was my first contribution. I did quite a few. Then I had a hiatus of like 5 years, and then another stop of 7 years, and then this was during the Corona lockdown that I did quite a few of them. All right, I'll keep it at that. See you later.